A quick look at the small C compiler, a C compiler written in C by Cain in Dr. Dobbs' Journal, Volume 5, May 1980. I've pulled the article up on the archives. As you can see, I'm on page 190 of 466. The title is A Small C Compiler for the 8080s. We scroll down to the source code. He explains how things work here. There's the beginning of the source code. Let's just go see how statements are handled. On the left-hand side here, we see the statement parser. Let's look at if, for example. And here, he's just got a big chain of if then else's, and he calls a function called amatch that looks at the input buffer to see if the next two characters are IF. And if they are, it returns true, and in that case, it calls a function called doIf, and then it sets a variable last statement to say that the last statement was a statement if. I think if we scroll down, I think doIf is down here. There it is. On this side over here, doIf is here. It's just a function. At this point, he sets up some variables. Then he calls a thing to generate a label. He generates the code to output the label. He then calls statement. So it's if expression, then followed maybe by an else, followed by another statement, is what we're going to be looking for. And he's going to be emitting code here. The things to notice in the parser up here, in parsing this if, he calls this function amatch if. So this big block of if statements, if, else, if stuff, is the actual parser, and the tokenizer is just a blunderbuss approach of just doing pattern of string matching on the input. If you think it would be nice to do the string matching only once and say assign a magic code, let's say 44, if it sees an if, that's what a scanner does. It does the string matching once, figures out what's in the input, and rewrites the input as a series of magic tokens, which in our case would be just numbers. He's not doing that here. He's just calling functions on the fly and doing it over and over again. And we can optimize that away by using a scanner. After you do this once, you find that there's nothing hard about it. There's just a lot of work, and you make a lot of mistakes on the way. So wouldn't it be nice to have a DSL to write a scanner for you? So if you were able to write in the DSL the things that you wanted to scan for, and then let the DSL compiler compile out to C code, maybe this C code here, a bunch of A matches, that would be what a scanner DSL does. The canonical scanner DSL is called Lex, and it uses a DSL syntax based on the theory of regular expressions, and that's where you get this really horrible DSL syntax, but it still saves you having to write all this stuff out by hand. In addition, after you've written the parser once, you find there's nothing difficult in doing it, but there's just a lot of it, and you can make a lot of mistakes. Wouldn't it be nice to have a DSL that builds parser code for you? And that's what Yak does. Yak accepts a DSL syntax. We call it BNF, or we call it a grammar. So if we follow that syntax, those syntax rules, then we can write out what we want, what kind of tokens we want it to match for. It matches for sequences of tokens, and we can tell it what tokens it should find in what sequence. The tokens were already produced by the DSL for lexing, for scanning, It produced a C program based on regular expression theory that ate characters from the input and converted them into numeric tokens that would take less work to scan. So you wouldn't have to do the scanning more than once at the beginning, and all the other subsequent passes could use the tokens, the magic tokens, like number 42 means if, stuff like that. And here, this parser, if it used the proper scanner, it would instead of a match if, it would say, is the next token number 42? And if it was, then it would do something about it. And if it wasn't, it would raise what's called a syntax error. It says you got stuff here in the source code that doesn't match up with what I'm expecting. And so I've errored out. Earlier compilers stopped immediately, and then they worked out ways of how can we find as many syntax errors as possible in one go so we don't waste your time. And that's really just more programming lore. Again, nothing very difficult, just a bunch of little details of how can you do this? When you get an error, what do you do? How many tokens do you skip? I guess one example would be you just skip tokens until you hit a new line token, and then you'd start parsing again and say, we saw an error already. What does this look illegal? And if it did, it would pick up, continue on until it found more errors or until it finished. When it finished, it would check to see were there any errors along the way. If so, let's stop now and just print out what the errors were. Let's scroll down to where it emits code. Let's look at, I think jump will be pretty straightforward in looking at some of this stuff. Basically, you can see this is just loads of C code that looks at characters one at a time, and scanning and parsing are ways of looking at the characters. One, pre-processing the input text so that you don't have to match over and over and over again, burning time and making the compile slower. This hierarchy stuff here is an encoding of the parsing a hierarchy in an expression and saying which parts of expressions bind more tightly than other kinds. You hear, in this case, we're looking at less than, greater, equal, and so on. We keep going. We'll find as we get deeper and deeper into the hierarchy, well, this is actually backward. It looks like it's backwards. No, higher 7. Here he's looking for shift operators. Here he's looking for minus operators, and so on. And basically he's just hardwired in the hierarchy of function calls, what order, what binding, how. He's hardwired what we now call the abstract syntax tree as a bunch of mutually recursive functions that walk what is in essence the abstract syntax tree and verify that the incoming syntax follows the rules of the syntax. Here's a really simple piece of output code. What he does when he sees an add, x plus y, he calls add, and then he emits the opcode DAD-D, which is the Intel 8080 instruction to add two registers together, and that's the assembler for it. As you tour through this, you're welcome to tour through it yourself in more detail. And that's the URL here. And you'll see there's nothing magical going on here. It's just there's a lot of code, and once you write it one time through, you go, oh, I could have abstracted this code this way and reused it and written less code over and over again. So that's what a scanner and parsers doing the semantic analysis. We saw basically semantic analysis hardwired into the codes, into the C code here.